Hey guys, it's Emil here. Today we're going to go over how to do a Fermi surface calculation. It's relatively pretty simple, a little bit more complex. Well, honestly, it's pretty much the same similarity as a band structure calculation. Same sort of process. So firstly, I made a directory called Fermi in my I made a subdirectory called Fermi, I should say. So from here, I'm going to copy, what am I going to copy? I'm going to copy this in card that I have. I'll include it in the tutorial that I usually I'm going to include it in my website where I have sort of the master tutorials. Okay, now I should have the in-car. I also need, I think that's it actually. And the in-car is going to look like this, where you have the magnetic moments, you have, again, this is a DFT plus U, and also it's spin orbit coupled, this calculation. So these are the, you know, things of interest here in your calculation that you need. You don't need spin orbit coupling. Again, you don't need the DFT plus U, or I should say the plus U component. You don't need the magnetism. Just these three. And I smear is going to be 0 because it's a rather large K points that's being constructed, I believe. And I do just need to look at the previous end card to see. Actually, I think I'm just going to use this previous out card or in card because I have a lot of particular. This is just what I'll do. I'll just do this. I'll just copy this over. Yep. Oh, that's all the same actually. Yeah, so I smear is 0, I charge 11 because it's reading the previous charge density. L orbit's 11. And that's going to allow you to see the. What is it going to allow you to see? I think the orbital states. I think it's orbital decomposed. Is it even L orbital? What? I orbit, L orbit, L orbit. L orbit 11, DOS car, and yeah, projectors. Okay, so it is decomposed here. All right, now we're gonna use VASPKIT for this next portion for the, for the K points generation. So it sort of works. It's gonna be different. It's gonna be slightly different to the actual band structure K points, but again, this is where the similarity comes in, right? So all I'm gonna want to do here is 26 Fermi surface. We're gonna generate a a K points file for the Fermi surface calculation. POSCAR not found. Okay, I should have known that beforehand. Job. POSCAR. I think that's it. No. I think that is it. Okay. And 261. 0.01 is generally precise enough. I'll take their word for it, and if you look at the K points now, it is quite excessive. So that's pretty much it. Oh, actually, I need the charge density file. Maybe we also need the wave car. Ooh, definitely not. Okay, so that should be it. I'm going to read this again. There's nothing here referring to the wave car, S-axis. I'm going to copy the wave car over actually, just so it proceeds a little bit faster. And again, this is a pretty big wave car, only because I'm doing a spin orbit coupled calculation, and that's very intensive. I think I already copied job. Now let me just go over this file, spin orbit coupling, and I'll name it Fermi. I have 36 cores. Let me double check the N core. N core is 6, K core is 1. L wave is true. Okay, so that should be it. Any problems, I guess we'll see them now. Calculation is all done. My post-processing, I like to use PyProcar. I find that it's really easily manageable. It's very well documented in terms of tutorials. So that's what I've been using, particularly for band structures, band structure plotting, as well as now Fermi surface plotting. So there's a variety of different things that exist already for visualizing your Fermi surfaces. And if you already know how to use them, that's all right. You can go ahead, because VASPKIT already uses, I believe, Fermi Surfer, as well as XChrisDen format, so you could generate them however you see fit. And if you want to sort of just go through it, it's just like this. So you know, read the Fermi, whatever, and it'll write your Fermi surface dot whatever. So you could put it into Fermi Surfer, and you could see I probably have already tried to do it. I just, again, I didn't really like it. I couldn't really get into it on the website version, as well as downloading it just didn't work right. So again, all I used was PyProcar. Now, if I remember correctly, all you need for PyProcar is obviously your Procar. And now I'm going to download this over to, I'll make a new directory. Yeah. I believe you're also going to need your outcar and your K points. I'm trying to check a folder in which I did this already. So I have the Procar, outcar, POSCAR, K points. I guess I'll just copy all of those over. I also have VASP run. Anyways, I tend to like this because it makes some really nice pictures. Oh, I guess you guys cannot see this. Maybe now you can. No. I have to escape from full screen mode. Let's remove these here. Okay, let's get off the news. Yeah, so again, this was an example that I had done, and you're able to decompose it into the orbitals, as I said before. This is the F orbital for uranium, rhodium, germanium. So the Procar is done. Now we're going to copy over again the outcar. And by the time that you will view this video again, I'll have these steps written out on my website. You could just, oh, wow. You could just pop over to my website. It's my first and last name.me. In the future, this might change to .github.io, but I'm going to see how much the .me domain costs because it's much shorter. So again, using VASP, and I continuously try to update this website. so it's as aesthetically pleasing and easily guidable uh, as it can possibly be. So I'm gonna head over to my drive. Yes. Ooh. Okay, and you can see it's getting full because I tend to not clear this out. I mean, I probably should, but again, let me just check the trash. I think I have quite a bit here that I will not need, and I'll go from 12 gigabytes to roughly what? Um, I'm not saying you have to use this. I just use it because, okay, didn't delete much. Again, I tend to use this just because I'm using a workstation. I just want to copy things over easy, and this is the easiest way for me to do it. So I have the pro car, I have the out car. Let's also do the K point and pos car. So I find that the trick is actually understanding what it is that you're plotting, because I've played around with this quite a bit, and I don't have a physics background, nor a sort of condensed matter physics background or a theoretical background. I'm coming at this from the perspective of a solid state chemist that wants to gain some sort of insight. So, that's how I've gotten into band structures, density of states, so on and so forth. And now I'm trotting into some unknown water, in this case being Fermi surfaces. But it's good because it keeps you on your toes, you continuously read, and you never get bored. So, again, that should be pretty much it. I'm going to head over to this. I'm going to refresh the page. I'm going to download the entire folder. And you're going to see, again, relatively heavy set file, or excuse me, directory, folder, whatever you want to call it. So it's downloading a zip file. And for the post-processing, again, I like to use VS Code because I visualize everything pretty nice. This is PyProcar. This is their Fermi surface stuff. And you can see it's very well documented. It's just a lot of sort of manual adjusting. So I like to, when possible, have different quote unquote notebooks, or however you want to call them. 7 minutes. Yeah, so this is quite a big file. It's 60 megabytes, I guess. It's 60 megabytes zipped. My Wi-Fi used to be fast. That is no longer the case. I think they downgraded my Wi-Fi here. Alright, so our folder's all downloaded. I'm gonna drag this. Okay, cool. That's fine. I'm gonna drag this here so you guys could see it. K points, out car, pos car, and the pro car. So from here, what am I gonna do? Well, I'm gonna open a directory, and again, this is going in from the I'll leave that over to the side. Let's see. I want to increase the size here. So, you're going to see this is completely based off of the tutorial. So hopefully when you look at the tutorial from PyProcar, oh, I just realized you guys probably haven't seen it. Excuse me. This is the PyProcar Fermi surface tutorial. So it tells you step by step how to do everything. It goes over this setup and data loading portion, the class, whatever, yada yada yada. So this is also you need your Fermi energy. So let me. Okay, that's good. Let's take a look at the Fermi energy in the DOS car. Fermi is going to be 8.126. (24301). And then the directory is going to change, right? Because this is we're going to copy the path name just like that. If you want to copy the path name on Mac, you don't know how to do it. All you do is double click on your trackpad and click option. That's to the left of the command, which is to the left of your space bar. Copy the path name just like that. And then boom. So you're going to apply symmetry, use cache is false, Fermi's adjusted, verbose is just the standard thing. I'm not changing anything. We're going to change that as well. This is actually 2 chunks of code that I'm sort of portioning. So this is the first aspect, this will be the second. And this will plot your Fermi surface as needed. So again, this is going to set up, this is going to create your Fermi handler object, and this will where your errors come in. So unexpected keyword argument verbose. It sounds French, so I'm not sure that's how you pronounce it, but we'll figure it out. La la la. Uh-oh. I'm not sure why this isn't. Okay, well, I guess that works. So we'll just remove verbose then. Oh, it's still loading, so I don't know. But I got this message. PyProcar stuff. So that's it. Took about a minute. And now this is the second portion. We're just going to do a basic 3D Fermi surface with band colors. Oh god. I don't want to X out of this because I'm too lazy. So this is step 4. And now I believe we superseded any possible errors. Oh wow. Oh god. Okay, so it's nice. This is interactive. You could zoom in, you could turn it, and you could see there's a lot, there's a lot going on. Yeah, there's quite a bit going on. You could turn your axis on, off. Yeah, again, I really don't know what I'm looking at, and there's quite a bit of theory to begin to know what you're looking at. So again, this uranium system is a highly correlated system. There's going to be a lot of interactions, especially coming out of the uranium F atoms. And again, we have spin orbit coupling turned on. So what's especially nice from PyProcar is that they do support spin orbit coupling, which complicates it because a lot of people, or excuse me, a lot of softwares don't support it. So we could do a parametric mode. I actually don't know if this mode works because when I did it before for what are we doing now? This is what? Yeah, uranium germanide. Okay, so previously I did this for uranium, rhodium, germanium. Yeah, okay, so you can see that the parametric mode in this case didn't work. Let's see if it works here. You never know, sometimes it could. Copy that path over again. And okay. And I have to double check the POSCAR to see which atoms are the uranium. So it's the first 4, that's good. And we're looking at the F orbitals. This orbital index is going to be 9 through 15. And again, you could feel free to scroll through the, what do you call it? The sort of API here. It'll tell you what indices, orbitals attribute to what. So these are, oh yeah, it's right here. So S is 0, P is 1, 2, 3. It's pretty intuitive. We're gonna see if this works. I'm not particularly hopeful that it will. Oh, okay, it worked. I don't see it. Oh, it saved here, I think. Okay, cool. All right, so this is this is how that looks. Um, oh, we need the scale bar, don't we? We do need that. Get rid of this, dude. Come on. Let's do show true. Oh, true. Hello? Okay. Show is already true, so it should be displaying it in the output. I guess not. It's fine. All is forgiven. So you could see the areas where there are the most, you know, F orbital contributions. They tend to be towards these two ends, respectively. The least amount being pretty much through the center of it. Again, if there is a physicist here who watches these videos, please feel free to reach out to me and help me because I'd really love to learn about these. I should be putting some more time and effort into understanding the theory behind it, but I'm not a theorist. Theoretician? Theorist? Theoretician. I'm almost sure that's how that's pronounced. Theoretician. Okay. Anyways. Yeah. So we could also add some interactive objects to this. Customize the appearance. So again, just play around. You could do a bunch of different saving options. You could also do a GIF. I think that's pretty cool. Trying to see what else is particularly important here. I guess, this is the F orbital contributions. Maybe I want to, if you want to look at the D orbital contributions, again, what you change for the orbitals portion is, we'll add 4 to 8. And you could see I believe there's a spin channel adjustment that you can adjust for, I believe, your spin up and spin down states. And then let's see our D orbital contributions and try to make any insight, really. Oh, wow. Yeah, okay. So you could see, yeah, the major contributions to your Fermi surface is obviously going to be your highly correlated valence electrons in the F shell. If we could try to make some, what is this? UG terminide. Okay. Where is this? Ferromagnetic. Is this spin orbit coupled? I'm going to assume yes. Yeah, and these are the band structure density of states. So again, major contributor is going to be the F electrons here. Primarily along the Fermi level, a little bit of contribution from your germanium, and I believe that should be all I really wanted to go over here. Oh, excuse me, that was the wrong. Here's a spin orbit coupled calculation. Yeah, this is the correct one. So again, primarily going to be your uranium F electrons. Let's see. Am I missing anything? You could see the projected band, pretty much the same. Actually decreased. Germanium contributions near the Fermi level. Mostly your uranium F electron, some D incorporation as well, your germanium. Yeah, so there's also, let's see. So I was looking at the parametric mode. I'm trying to figure out how I got those squiggles. There's a 2D handler as well, however that's going to be. Yeah, dealing with spin in PyProcar Fermi 2D. You could try to visualize your spins in your collinear and non-collinear cases. We did a collinear calculation here. That was in a previous video. So again, I'm going to go over here. Oop. I'm going to go over here and find where I did something similar. This is it. This does your spin. Now your collinear stuff, 9 through 15, this is good. This does need to change. And if we look at this, magnetic atom, all thin transition metal. Oh, interesting. So they did only one atom in this one. So they did the d orbital. Okay. Let's just do it and see what happens. Okay. So again, sometimes you'll see these errors. I'm really not sure what it means. Could be missing a file, which I doubt in this particular scenario. As we seen that it worked. Oh, the Fermi energy we never corrected here. Did we? What? Okay. Yeah, so I forgot what I was doing actually. I leave for 1 second, everything goes to failure. Yes, the Fermi. Actually, Fermi handler should be good so we don't have to keep putting in the Fermi energy. Actually, in this case we do because it's a different handler. So this could be the problem. I doubt it. This is nice. You can see the energy relative to the Fermi as well. Maybe this will work. So this is one atom that they're viewing. You could also plot individual spin channels. Like I said, 0 is spin up. 1 is going to be your spin down. They had a problem here, and what was that? Interesting. Okay. Non-collinear. You could do spin component properties, your X, Y, and Z, your spin texture mode. This is still working it out. Advanced spin texture. Yeah, there's a variety of different options here, which are fantastic. And let's see the following. Your KZ plane slice you could adjust as well. It always looks like they only project onto a singular atom. Individual band analysis. This is fantastic. And again, oh, here we go. Cannot reshape it. Yeah, I'm really not sure what this means. Let's go back a little further. Maybe one of these could work. Okay. Is this not the same thing? I'm almost positive it is. What was... Oh. Spin texture true. Okay, so that didn't work. What happens if I put spin texture true here? Will that also fail? Probably. Most likely, actually. In that case, instead of doing parametric, let's just do plane. Let's kill this. We'll change this to plane. Ooh, okay, that's good. Restart kernel. Okay, so we have to set this up once again. Do we? Maybe. Alright, so again, this failed. If I could do a little bit more digging, I'll probably figure it out, but I don't really feel like it. Anyways, give this a try, play around. Again, PyProcar is quite a pretty powerful and useful software here, very interpretable, very well documented. I can't give credit where it's due more than this. And the VASP calculation is pretty straightforward. Again, if you guys have any questions, feel free to comment down below, and we'll go over some other things. Thanks again for watching, and please, again, any physicists out there, please reach out to me if you know how to interpret these results. It'd be very beneficial for my research.